Continuing on with transformations of our graphs, let's look at dilations. Now, that's where we stretch our curves. So a horizontal stretch or a horizontal dilation, so we're pulling it out or pushing it in, that's when we replace x with x divided by some constant number. Function x over a it becomes. Now if we've got that, that means stretching by a factor of something greater than 1 means pulling it out. Now if that factor is a fraction, so like a half, well then it has the reverse factor, pushes it in. But basically, if that number is bigger than 1, the curve should become shallower. So when you pull it out, it's going to become a shallower curve. The domain might change. I mean, if it's all real x, it's not going to change. It's still going to be all real x. But if it was going between two certain points, when you pull it out, it'll go between two different points. So the domain. The range won't change though. All we're doing is pulling it out. We're doing nothing to the height of the function. The reverse one, the vertical dilation. Now that's where we stretch it the other way. So it's the y values we're affecting. That's what's going to change. So we replace y with y on a. So y on a will be function x, although we normally see it as y equals some constant times function x. So we stretch it vertically by that factor. Again, if it's greater than 1, we stretch it out. But now, because we're stretching it vertically, if you think about that, it becomes a steeper curve rather than a shallower curve when we stretch it vertically. And if it was a fraction, so half, again we'd push it in, go the other way. The domain won't change, but the range might now. So the same idea. Alright, let's do some. Start with a very simple one, a straight line. We know y equals x, our standard straight line goes at 45 degrees. If we were to go y equals a half x, there's y equals a half x. We could actually think of this one in two ways, because I could say, look, I've divided x by 2, so I've stretched it out and made it a shallower curve. But of course with this one I could also say, hang on a sec, no, what I've done is I've stretched it vertically, because I could think of this one as 2y equals x. So it could be grouped with either one in this case. But if we stretch it vertically, because we'd go y divided by the half, it's a number that's smaller than 1, so we'd push it down, and again we get a shallower curve. Y equals 2x would then be on the other side. Now the factor's going the other way, so we're stretching it up or we're pushing it in, either way. But that's a straight line. The same happens with all our functions. Now in this case, our standard parabola, we've got y equals a half x squared. Now in this case, it definitely is grouped with the y. It's not grouped with the x, because x is squared. So that half, I can think of it as y divided by a half, a number that's smaller than 1. So I'm pushing it down. It should become a shallower parabola, like that. Y equals 2x squared, which would be y over 2. It's a number bigger than 1. That would be stretched out. It would become a steeper curve. X squared plus y squared on 4 is equal to 1. So we haven't done anything with the x this time, but the y squared on 4. So it is our basic circle we're starting with. X squared plus y squared equals 1. But it's the y values we have changed. So what we've really done is said, we've stretched it vertically by a factor of 2, because y squared on 4 would be the same as y on 2 all squared. So we replace the y with y on 2. So by a factor of 2, which means if I'm stretching out by a factor of 2, those y-intercepts at 1 and minus 1 should now go to minus 2 and plus 2. We end up with an ellipse. So you notice here the domain has not changed, the range has, because it was the y values we were playing with. Here's one from a couple of years ago. They gave us this particular graph, and we had to sketch the graph of 4 times function 2x. And they wanted to know where the x-intercepts went and how that turning point got changed, and so on. Y equals 4 times function 2x. There's our curve. Now, that becomes y on 4 is equal to function x on a half. I look at it that way so I can see what the dilation factor is. So I now know I've stretched it horizontally by a factor of a half. So I've pushed it in, and all those x values should be halved. I end up with that. The x-intercept is now 3. That turning point is now at an x value of 2. I've halved all of those points. But we've also stretched it vertically by a factor of 4. So now I'm pulling it out, which means that y value of -8 is going to change. It now goes down to -32 because it's been stretched down by a factor of 4. So that would be our new graph. Enlargements. How do we enlarge a graph? Well, that's when you apply the same dilation, both horizontally and vertically, and have the effect of getting the same shape, but just a bigger size, or a smaller size, depending on what the dilation factor is. So function, well, the x and the y values, what I'm basically saying here, would change to x on a and y on a. So every point on the curve would change that way. Our circle, x minus 1 squared plus y plus 2 squared equals 1, is enlarged by a factor of 2. Now this works when it's the origin as the centre of enlargement. Find the circle's new equation. So everywhere I see an x, I'm replacing it as x on 2. Everywhere I see a y, replacing it with y on 2. Play with that, and eventually we get this. Now notice they didn't actually say draw it. They just wanted the new equation. So x minus 2 squared plus y plus 4 squared is equal to 4. Not all transformations commute. Now there's an old word in maths, the commutative laws, which you've probably even forgotten about if you've ever seen it all. It just means basically the order that you do things in. Can you commute those orders? It can commute if the order of your operation does not matter. So for example, multiplication commutes, because 2 times 4 times 3 is the same as 3 times 2 times 4 is the same. You can move those numbers around and you still get the same answer. So addition and multiplication, they certainly do commute. So you can swap the numbers around. Subtraction and division do not commute. 3 minus 4 would not be the same as 4 minus 3, and 3 divided by 4 is not the same as 4 divided by 3. So they're the basic operations and what we're talking about with commuting. Well, transformations. Transformations do commute with an exception. Dilation and translation in the same direction. Let's see an example. There's a random graph. And if I reflect it, so I've translated it, if you like, via a reflection. So I've reflected it in x equals 0, then I've shifted it right. So I did a reflection, then a shift. And that's what we looked at yesterday when we talked about reflecting in the line x equals a. We did a reflection, then a shift, and I said do the reflection first. That's why. So that's a dilation of -1, if you like. The second way of doing it, if I was to shift it right and then reflect it in x equals 0, I get a different curve. So the order mattered. It doesn't commute. Determine the equation after y equals x squared has been, first of all, shifted up 1, then reflected vertically. So the x would go to x squared plus 1. We've shifted it up 1. Reflecting it vertically, a vertical reflection was minus the function, so the complete function. So we got minus x squared plus 1, which is y equals minus x squared minus 1. So that's if I shift it up 1 and then reflect it vertically. If I went the other way around, reflect it vertically, then shift it up 1 unit, the x squared would go to minus x squared, but now I shift it up 1 and I get a different equation. Y equals 1 minus x squared. So again, illustrating the difference of the order matters. So 3h and 3i.